Okay, so we're continuing on with probability here. And so what we've got is we're going to look at Venn diagrams and two-way tables, which can be used as a display of probability. So let's just go through it. So we're going to talk about, they're going to talk about set notation, which is just like symbols used. So when we talk about it, so if you remember yesterday, remember we said the set of elements, we put them in those curly brackets and things like that. So they're just talking about set notation. And instead of writing out, say, you know, the probability, you know, when we said like the probability that it's not A, instead of writing all that words out, we shorten it and we give it little abbreviations, like little words, and that's what set notation is. So we're going to see a few of those symbols. Don't worry. When we come across them, we'll explain it. So don't worry too much, but we're going to look at this Venn diagram. So a Venn diagram illustrates how all the elements in the sample space are distributed. So if you look, we have we have a set of, say for an example, let's put a little example. So say we had a set of, say the dice, you know, so the dice we could have the 6 options, yeah, that's the outcomes we could get. If we rolled a dice, we could get a 1, 2, 3, 4, 5, 6. So say I said the probability of A was equal to getting an even number. So would you agree that would be, this would be 2, 4, and 6? Would you agree? The probability A. And say I said the probability of B was was the numbers above 4. Okay, so B would be 5 and 6. Would you agree? So what you happen is we're going to display it in a Venn diagram. So say we had the probability, so we put all the numbers. So here's A and here's B. Now, A could be 2, 4, and 6, but B could be 5 and 6. Which one are they both in? Like, say, both groups. It could be, I get a 6. So 6 goes in the double area. Okay? Now, A can also be a 2 and a 4, so that option's in there. And B could also be a 5. Okay, what are the other numbers that I haven't, is there another option I haven't done that isn't in my diagram? Out of all my options, 1, 2, 3, 4, 5, 6, 3 and 1. So they're not in those probabilities, they're not in those events, so they go out there in the out area. Okay, so this is where all elements, they'll use that little symbol, are within the big square. Okay, so that's what we're going to do. So when we're going to look at things, don't worry too much about that empty set, but this one, I'm going to highlight this. This intersection is this bit here, yeah? It's both of them are in. The intersection is that bit. Now, instead of me writing out intersection and saying the intersection, can you see this symbol? That's the symbol for intersection. So it's the one that's in the both, yeah? In both events. So they're both in event A and event B. Event A was an even number. Event B was a 5 and a 6, okay? Then we have what we have the other one. We can have this union and see how union is, and you can remember union because it's the U, it's the up way. Now the union is all of it, so all A and B. So it's actually talking about all of that, yeah? So the union is that one. So if two sets are mutually exclusive, what does exclusive mean? If I've got an exclusive thing, yeah? Yeah, only one. So if they're mutually exclusive, that means they have no numbers in common or no elements in common. So let's draw a diagram underneath it so that we understand. That would mean like probably this would be A and this would be B. None of them would be interacting. That's what mutually exclusive means, all right? Now, what they start to talk about, they start to say, you know, I had probability of A was all the even numbers and probability. Then they're going to say, what's the probability of it not being an even number? Or so they say not A. Now, instead of writing out all of that, they start to write this symbol here. See that thing? So this means, see with the dash, not A. So everything else but A. Okay, so for my like above example, everything that's not A would be all the odd numbers. So it'd be 1, 3, and 5. That's everything that's not A. Okay, now what they're saying, if you want to find what the probability of not A is, you take 1, because 1 means it's going to happen, and you minus the probability of A. So that makes sense. If I had talked about the, say, head or tail, say the probability of A is a tail, so is that 50%, 0.5? Yeah, when you flip a coin. What's the probability that it's not a coin, not a tail? It's 0.5 as well, isn't it? You're 50-50 chance, so that makes sense. So that's what we'll do, but we'll always think. So let's just go around. There's a few things. Don't worry about, I think. This just means like the number in A. It's not the elements, it's the number of elements. So say for our example of the dice, the number of A is actually 3 because it was A equaled even numbers. Remember, so if we said that, it was 2, 4, and 6, but there's actually 3 in there. There's 3 options, so that's all that means. But don't worry, let's just go, keep going with the diagram. So we've sort of explained this already. So here we've got another bit of a diagram. So I said this bit was the intersection. So we saw that, so we know there's the intersection of the two, and they're just pointing out. So if you let's just write it in words. See this bit? It's not A, but the intersect. It is everything in B. So it's what's in B, but not A. Okay, so maybe sometimes it's a bit easier if we just write it out what it actually means. So this one, see, it's not A or not B. It's not in any of them. Before we had 1 and 3 and all things like that. So we've got all these symbols, and that's just some explanations. We will work it out when we do them ourselves. This is really one we need to just keep practicing, and then it sort of makes sense. So we could do it in a Venn diagram. Then they also look at the two-way table. So a two-way table will either, this is when they talk about the numbers. So say here, I have there's one element that's in both A and B, the intersection. Now there's 4 elements that's not. So this is all what we're doing. I reckon once we do a few examples, we're going to see this. So let's just get into it, and then we'll see how we go. But they're always there for help. All right. It says, let's have a look. On the Venn diagram, like the one shown, shade the region that's represented by the following. So I'm going to draw just little diagrams next to it. So if we want, so my first circle is A and B, okay? If we're going to shade, I'll shade in yellow, just so you can see. So if it was A only, you have to highlight just the whole yellow circle, or whole A circle. if it was just B, so A and B, you would highlight all the B. Now, here, the next one, they want the intersection of A and B, so that's just the bit in the middle. If they ask for the union of A and B, that's everything, so you colour the whole two circles like that. All right, if we have A only, so A only, so not, it can't be the intersection, it's just what A is. That is that, just that side. Don't colour the intersection in. And if it's B, if it's B only, it's only going to be, sorry, that was a little bit. It's only going to be what's B, okay? All right, if we do just down here, neither A or B, so say they're A and B, that's going to be all this outside area, like that. And remember, this dash is everything that's not A. So if I'm calling the first circle A and the second circle B, everything that's not A would be part of that B circle and also the outside. All right, I'll just pause that. Okay, now that's quickly asking us what symbols are used. So if we have a null set, we use that symbol. If we want to write A and B, that is like saying union, A union B. You want all of A and all of B. If you want, actually, I'll tell a lie. That's A intersection, A and B. If you want A or B, that's when it's union, A union B. And the same with here, you could say A union B. This would be if I had a third circle, a third event. So we just write like that. So it says decide if these events are mutually exclusive. So remember, if it's mutually exclusive, no common elements. Okay, so we look at this first set here. Is there a number that's the same? Isn't there 5 in both? So that's no, that is not mutually exclusive. If I looked at the second one, they're saying all the numbers from -3 up to 4, and they're saying all the numbers from -11 up to -4. Are there any common numbers there? No, they're not, because this one finishes here and then this one starts. So will they have any in common? No. So this one, is it mutually exclusive? Yes. Mutually exclusive. And the last one, let's have a look. If we look at it, prime numbers, if we remember prime numbers is things that can't be divided by anything else but itself. So you think 2, 3, 5, 7, and then it would be 11. So, but if I do even numbers, isn't it 2, 4, 6? So is there going to be a common one? We can already see a common one, can't we? Which is 2. So is this mutually exclusive? It's not mutually exclusive. Okay, so let's stop that there.